you want to name a structure, first thing you do is find the longest continuous carbon chain. That's going to be the basis of the name. The longest chain beginning at the end of the chain near a substituent. Name the groups attached to the longest chain as alky groups, or we'll see as halides or whatever groups you got on there. Number the main chain carbon atom to which it's attached. Write the alky groups in alphabetical order regardless of their position on the chain. And so here we saw that we could maybe choose chains of lesser length. We want to start from this end where we have the substituent on the second carbon. If we started here, we'd go 1, 2, 3 and have our first substituent on the third carbon. So we come up and we name this 3-ethyl 2,4,5 trimethyl heptane for a 7-carbon chain. Name the groups attached to the longest chain as alky groups. Give the location of each alky group by the number of the main chain carbon atom to which it's attached. Write the alky groups in alphabetical order, regardless of their position on the chain. So when you have more than one of the same substituent, we can use tri, di, tetra to tell the reader how many of those groups you have. So here we have a 10-carbon chain with 3 methyl groups on it. So at carbon 2 and 5 and 7 we have methyl groups, so this gets named 2,5,7 trimethyl decane. Isogroups. Don't normally use these a lot, but here's 2 alky groups. Propyl gets used quite a bit. Isobutyl you can use as well. We're going to see this thing called a complex substituent here in a second. So, finding the longest chain. So I see students sometimes go 1, 2, 3, 4, 5, and they name this 2-ethyl pentane. When you name this 2-ethyl pentane, you don't get any partial credit. If you named it 1, 2, 3, 4, 5, 6. If you name this 4-methyl hexane, you'd get partial credit, but you'd lose points for the numbers not working out the way they should work out. All right, so here we might see some difficulties when there are 2 chains of equal length, and of course they're the longest chain you could find in the structure. It says here, use the chain with the greatest number of substituents. So if I encounter this, we'll see when in an example there's no boxes leading you and helping you. I might go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right, and then of course when I got 7 this way and that way, that was a bit redundant. So which do I want to use? If I look over here, I have a methyl, and an isopropyl. When I go this way, I have a methyl, and a ethyl. So I got 1, 2, 3, 4 substituents there. I have 1, 2, 3 substituents there. So 7-carbon chain in each instance. One chain has 3 substituents. The other has 4. So we choose the one with 4 substituents. And could probably name this 1, 2, 3, 4, 5, 6. 3, 4, 6 trimethyl 5-ethyl heptane. And there we get it named. Oh, I messed up. I did methyl first. I didn't follow the alphabetical rule. So, and I numbered from the wrong side even. So here our first methyl comes at number 3 carbon, but if we go this way, we get a substituent at number 2 carbon. So here, now this thing is properly named 3-ethyl 2,4,5 trimethyl heptane. Number the longest chain beginning at the end of the chain that gives you the closest substituent. So a complex substituent. So here's this thing's an alky group. It's attached to something else. and I look at that, it doesn't look like isobutyl, isopropyl, it looks like a mess. So I'm going to name it as a complex substituent, and that means I'm going to find the longest carbon chain. 1, 2, 3, 1, 2, 3. Looks like a 3-carbon chain. Looks like it doesn't matter if I go that way or this way. I'm going to have a methyl group on number 2 carbon, and I'm going to have a ethyl group on number 1 carbon. And it says here complex alkyl groups are named by using the longest carbon chain, and carbon number 1 is always the one connected to the other piece of the molecule. We had a big carbon chain out here and this thing was attached. And so we call this thing 1-ethyl 2-methyl propyl. It's a propyl group. This thing here, 1, 2, 3, 4, so it's going to be a butyl group. And then I look at all the substituents and name it 1,1,3-trimethyl butyl. And maybe it's cyclohexane or something else this thing is stuck to. Any questions thus far? Alright, so here is that first one we just looked at. 1-ethyl 2-methyl propyl. Alright, so here's a big mess. Now if I didn't have all these boxes, I'd probably start out 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright, then I might go 1, 2, 3, 4, 5. 1, 2, 3. Alright, so first thing you're going to do is find the longest chain and number it in the direction that gives you the first substituent, the lower number. Alright, so here is a ethyl group, and here's this mess we couldn't name otherwise. So this becomes 3-ethyl 5, 1-ethyl 2-methyl propyl, no name. Alright, so here's this mess. 1,1,3-trimethyl butyl. Stick it on this thing. We're going to have some upcoming slides where we talk about naming cycloalkanes. So here's this cyclooctane, 8 carbons stuck together in a ring. Cyclooctane. Carbon number 1, we have 2 methyls. 1,1-dimethyl-3, parentheses, 1,1,3-trimethyl-butyl cyclooctane. Any questions? So there's one complex substituent that I don't like to see students use, and that is 1-methyl-ethyl. You want to say isopropyl. You don't want to say 1-methyl-ethyl. So you need to know your propyl alkyl groups and all your butyl alkyl groups. If it gets more complex beyond that, then you can use the complex substituent method. Any questions on those substituents? All right, so here's a good one. Nothing to guide us. So I'm looking at this, and I'm going to just randomly start out 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. All right, I'm getting an octane there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Looks like here's my longest carbon chain, right? 1, 2, 3, 4, 5, 6, 7, 8. Some form of octane. 1, 2, 3, 4, 5, 6, 7, 8. Got a number there. 1, 2, 3, 4, 5, 6, 7. Alright, I messed up. 1, 2, 3. I either have a methyl group at 3 or, ooh, look at this way. 1, 2. So I'm thinking this is looking like 1, 2, 3, 1, 1, 3 trimethyl, and then, ooh, I messed up. 1, 2, 3, 4. So 1, 1, 3. I gotta figure out whatever that number is. And here's this 1-methyl-ethyl. Students want to use a complex naming system for this alkyl group. And I said, don't do that. This is isopropyl. So what I should do is have some scratch paper. To me, this looks like 1, 1, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. So there it is. 4 isopropyl. That was a senior moment. 1, 1. All right. 2, 2, 3, and 2, 2, 3, and 6 tetramethyl. All right. So 4 isopropyl, 2, 2, 3, 6 tetramethyl octane. So let's leave nomenclature for a little bit and talk about alkanes. Where do we get them from? Petroleum products, for the most part. I suppose nowadays there's some non-petroleum sources, but it's just so cheap to pump the stuff out of the ground. So fractional distillation will separate the crude oil into mixtures of alkanes with a range of boiling points. Think about the Sinclair over here east of town, northeast of town, by the highway. Before that there was a Amoco. So let's just look at some physical properties of alkanes. So we add more and more carbons, we're increasing the London dispersion forces. So the light alkanes like methane, propane, and butane you find as gases. Octane, it's a nice liquid. So heptane, hexane's a liquid at normal ambient pressures and temperatures. So the isoalkanes have less surface area, less London dispersion, so you see it a little bit lower. But for the most part, as you put more and more carbons on it, you're increasing the intermolecular forces, larger boiling point. Here's just kind of an interesting thing. Melting points increase as the carbon chain increases. We just explained why that is. Alkanes with an even number of carbons have higher melting points than those with an odd number. Somehow they pack up better. Alright, so here's a dodecane, C12H26, a long chain alkane. That's going to have a low boiling point. Maybe it's good for asphalt or something. So something they might do over at the Sinclair is they heat this up with a catalyst. And notice here's 2 hydrogens, because if we break this somewhere, we'd have a CH2 and a CH2, and we need to add 2 more hydrogens. So now if you sum these up, you can see a 12 carbon chain. And if we didn't do that, if we just chop this in half by using a heat and a catalyst, this would be just catalytic cracking. Now you can see that our carbons and hydrogens have been conserved. 5 and 7 sum up to 12. 10 and 16 sum up to 26. 12 and 16 sum up to 28. 28 is too larger than 26. So there's where the 2 extra hydrogen came from. Alright, so if you have a carbon chain that has like 35 carbons in it, that's good for making asphalt. It stays hard. And maybe especially if you're like a motorcyclist on a hot day, you pull up your nice motorcycle on a new road with the kickstand down. You're always afraid your bike's going to turn over because the asphalt heats up and gets soft. So 2 to 4, butane lighters, propane heaters, liquefied petroleum gas. That's what LP stands for heating. The number of carbons, 4 to 9. 4 is stretching it. Gasoline. Number of carbons, 8 to 16. It's like your kerosene. Sometimes I use kerosene and diesel interchangeably. Heating, jet fuel, and then large change. Think motor oil. Looks like Vaseline, paraffin wax. This slide's kind of a review, but we're going to look at how sigma bonds can rotate. So here is a ethane, and I can rotate these bonds. I don't know if this can. Here's the sigma bond rotation of ethane, we might see some interesting things. Eclipsed and staggered. Eclipsed and staggered. That ought to be enough of that set up, hopefully by the end of this week. So when I rotated this, what we had was different conformations of ethane. So we say ethane has some conformations. And what is a conformation? They exist due to sigma bond rotation. So how might we distinguish one conformation from another? One way, is by this thing called a Newman projection. So when you want to draw a Newman projection, I say it has two parts. It has the peace sign and the ping pong ball. Peace sign and a ping pong ball. The peace sign doesn't have to be in the peace sign position. But what you want to realize is the first carbon you look at, the one that's closest to you is the peace sign. The one that's further away from you is the ping pong ball. A Newman projection is a great way to judge the stability of different conformations of a molecule. So you saw me spin it, and I said the words eclipsed and staggered, eclipsed and staggered. And there's an energy difference. So here's potential energy, and you can see in the eclipsed position that's molecule has more energy than the staggered position, and it's about 12.6 kilojoules per mole. And so the torsional energy of ethane is lowest in the staggered conformation. The eclipsed conformation has this energy difference, and at room temperature this barrier is easily overcome by the molecule, and it's rotating constant. Next up, propane. So when I look at it straight down like this, there's the peace sign, here's the ping pong ball. I'll do it for the camera. Peace sign, ping pong ball, and this thing rotates in some different conformations. So there's an eclipsed form, staggered, eclipsed again, staggered, and eclipsed. So this Newman projection here is in the eclipsed conformation. And now we see a greater energy difference, and that's because this methyl group occupies more space than hydrogen, and so we call this a torsional strain. Because it's not like the stick drawing. These things are actually have big electron clouds. It's kind of hard to define where it stops, where it begins, but there is a strain between these. So we see it's gone up by a little bit. We're now up to 13.8. We're just the ethane was 12.6. Now on to butane. Here's the butane, and if I look down the C2 and C3, of course here's a very eclipsed. Here's a staggered. Here's an interesting staggered. Staggered, and here's a super duper eclipsed. We probably have a better term than that one. But you can probably imagine this has the highest energy, or this one has the lowest, and then we have second highest, and some in between. So butane has two different staggered conformations. We call one of them gauche and anti between the methyl groups. The eclipsed conformation, where the dihedral angle between the methyl groups is 0, is referred to as totally eclipsed. Here's the totally eclipsed. Gauche is a form of staggered. It's higher in energy than the anti-staggered. And so here's an eclipsed. So you should have seen me rotate all of those. Here's what we really want to look at. So here the totally eclipsed is the highest in energy because these two methyl groups take up space. These big electron clouds push and they put the torsional strain on this bond. See how it makes it flex. Alright, so then when we go to this one staggered form that we call gauche, We've relieved that torsional strain. All right, then we rotate this some more. Now we're in an eclipse mode. We have a methyl and a hydrogen, and a methyl and a hydrogen eclipsing each other. Rotate this down one more. Now these methyl groups are as far apart from one another. We call this anti, and so this is the lowest energy conformation when this dihedral angle is 100. And then we repeat these as we get back around 360 degrees. Gets us back to totally eclipsed. So steric strain, this kind of interference between two bulky groups is called steric strain or hindrance, and that gives rise to a torsional strain in the molecule. This pushing here of these two groups. Notice the artist drew them nice and big here. Model kit doesn't do it justice. And here's the space-filling model. That might give it more justice. We call this steric hindrance. So when you have a big long alkane, like octane, here it's drawn in such a way that this group is anti with that group, this group is anti with that group. So nothing is eclipsed, and that would be a preferred low-energy conformation. The higher alkanes resemble butane in their preference for anti and gauche conformations about the carbon bond. Cycloalkanes, how do you name them? So I alluded to this the other day. I like to jump ahead. Cycloalkane is going to have a generic formula of CnH2n. 3-carbon cycloalkane, kind of rare. 3 twice is 6. Cyclohexane, 6 carbons, 6 twice is 12. If I broke this, I'd need to add 2 more hydrogens. That's why the alkane has the +2 here. 2n plus 2 on the H. So if we can count the number of carbons and come up with propane or hexane or heptane, we just put the prefix cyclo in front of that. So if we're going to figure out our nomenclature on cycloalkanes, once again, don't try and call this 1,1-dimethyl ethyl. No, you want to have all those alky groups named up to the 4 carbons, and this is tert-butyl. And the day I was gone, I gave you a lecture for one of those days that goes over these alky groups. All right, so this is just methyl cyclopentane. 1, 2, 3, 4, 5, 6, 7. A heptane, cycloheptane, and I got a tert-butyl. Why is it tert? Because the tertiary hydrogen was removed off this tertiary carbon. All right, here, this doesn't look like any alky group. Maybe this looks like an isobit, but then what about that? All right, doesn't look like any of those you saw in the video, so we'll use the complex substitution convention. 1, 2, 3. All right, so this is going to be a propyl. And I got a methyl there and methyl there, so 1,2-dimethyl-propyl cyclohexane. And since there's just one group on the ring, we don't need to use any numbers. Alright, now we got multiple groups. If there are 2 or more substituents, number the main chain to give all substituents the lowest number possible. What does that mean? Well, on this first thing, why when I go 1, 2, or more importantly, the first thing is we don't want to go 1, 2, 3, 4 and have this 1 ethyl 4 methyl. We want to get it so we get the lowest numbers possible. But I would start this 1 here just thinking to myself, alphabetically, we're going to go ethyl before methyl. All right, so I'm going to start numbering the ring here, number 1, and then I'm going to go around this way, counterclockwise versus clockwise, to make this 2 instead of a 4. So we properly name this 1-ethyl 2-methyl cyclobutane. All right, once again, look at these substituents before I get going. So I want the lowest grouping of numbers. So here I got multiple groups on one carbon. Here I got one group. More than likely, this is going to be where number 1 needs to be. Then I go around the ring this way to make this a number 3 versus 1, 2, 3, 4. I would want to call this 1,1,4-trimethylcyclopentane if I can name it 1,1,3. All right, here is got a bunch of things going on, and here it doesn't matter which way I go around the ring, and I'm going to choose this to be number 1 because I got 2 of these. If I chose this to be number 1, I'd have 4,4-diethyl-1 isopropyl cyclohexane. There are 2 or more substituents. Number the main chain to give all substituents the lowest possible number. Once again, I don't like it when students name this 1-methyl-ethyl. No. That's why we learned isopropyl. Well, my video, I left out the propyl, then I made another video, and then I was too tired and lazy to edit it in after I spent all that time editing the first one. Isopropyl. 1,1-diethyl-4 isopropyl cyclohexene. When the substituent is a cycloalkane, the cycloalkane becomes a substituent when the acyclic portion of the molecule contains more carbons than the cyclic part, or when there is a more important functional group in the molecule. Somehow I think there should be another or in there. Alright, so you're thinking how I'm going to name this. Luckily you got this first rule. You wouldn't want to name this as a complex substituent and then try and name it cyclopropane. So this is clearly more carbons than the 3 here. So we're going to name this as some derivative of octane. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, that's why we number the chain going this way. So we have a methyl at 3 and a cyclopentane. Chop off the AN and add LY. That's our convention for alky groups. So 4-cyclopropyl 3-methyl octane. Here's one that might throw students off. Sometimes they start this as carbon number. Alright, then you get the wrong number of chain and you don't get any partial credit. So this is a substituent on carbon number 1. You don't want to make the ring carbon number 1, but students like to do that, so don't do that. So methyl group at 3, methyl group at 5. So this becomes 1-cyclobutyl 3,5-dimethyl hexane. Here's something. So we're going to name this as the substituent, and this as the cycloalkane. So we have a cyclohexane, and we have cyclopentyl hexane. All right, well that burned up all